Okay, so what this equation does, okay, is it puts into in math what we saw in that video, right, where things were rolling uphill almost, right? And it's a change in the potential energy that we see. Okay, so a roller coaster, and this is what I was alluding to when we first started this unit, is typically referred to as a gravity ride. Okay, work is done on the roller coaster to raise it to the top of the first hill, which is the highest potential energy, right? Okay, highest potential, which will create kinetic energy as soon as it's released, right? So we learned on Friday, if an object is in motion, has a velocity, and has some mass, it'll have kinetic energy. Okay, so ultimately, like the way obviously roller coasters move around the track, right? So the way that the whole principle works is that we can go up hills to create potential energy so that they can go down hills to create kinetic energy. And that's the whole principle of what we call like a roller coaster or a gravity ride, right? So we're going to develop kinetic energy. Okay. Okay. And then it has, like the roller coaster is going to have potential energy because of its elevation above the Earth's surface, right? Okay. And then we saw on Friday, like we could measure the amount of work a force does by looking at how it's applied, whether it's perpendicular or in the line of the motion. We learned that perpendicular forces don't do any work, okay? But forces acting in the same direction as the displacement. In this case, all we've done was we looked at some questions going horizontal. For gravitational potential energy, the work that we'd be measuring would be like the Coca-Cola case question, right? Where like the employee lifted it up to the shelf and then a customer came along and lifted it down, right? So all we're dealing with is this like change in the Y value, which you might see as being H, right? For height, we might come across that. Okay. Anybody have any problems so far? And so we could see, just based on what we looked at on Friday, the work done in increasing the elevation of an object is equal to the change in the gravitational potential energy. And that's what this is saying, right? Work is equal to the change in Eg, which is gravitational energy, which would be equal to that. You could even go one further and say this is going to be equal to mg y final, or y2, minus mg y1. That would be the change in, right? y2 minus y1, change in height, like rise for slope. Okay, that's how we could figure out the amount of work that gravity does. Okay, any problems so far? It's a pretty easy concept. It's easy, but then we can apply it to like complicated questions, and all of a sudden like we have this simple approach that solves complicated problems. That's what we're going to do tomorrow. Okay, we just need to put all the stuff that we've learned so far in the first day together with the second day, and all of a sudden we get this third day of lessons. Okay, so there are a few important points to remember in using this equation, right? The equation determines the change in gravitational potential energy and does not determine the absolute value. Okay, the absolute value indicates, if you guys haven't dealt, well, I'd imagine you would have seen something like y equals the absolute value of x. This, you guys would have had a graph like this, where every y value was positive, right? Didn't have any negative y values, right? So that's what this is saying. It's not determining an absolute value. It's determining the actual potential energy. So we can have negative values. That means something to us. Okay. The value of delta y is the vertical displacement of the object. Okay, and this means that the horizontal path of an object follows an increasing its vertical height is not significant. I don't think that's written very well. It just means that, like, you know, we're not really interested in the motion in the horizontal direction and for potential energy. I'm interested in, like, how is the height changing? Okay, that's potential energy. Okay, the equation may only be used when delta y is small enough, okay, that gravity does not vary significantly over delta y. Okay, so what that means is if we were to, like, get above, I don't know, some atmospheric level on Earth, right, such that we're starting to get weaker and weaker amounts of gravity, now the potential energy changes, right? It changes because you have this gravity term in there, right? So this equation is only applicable for delta y values where the g value, negative 9.8, is still applicable. Okay, it doesn't apply in space, right? Because the g value is different. Okay, it could work if you were on Mars. If I give you a question like on the kinematic summative, right, where we had, like, the g value on Mars is negative 1.4 or whatever it was, right? Then that would be fine as well. But as soon as you get into space and the g value changes, you can't use this anymore. Okay, because the object is being influenced by other gravitational fields at that point. Okay, so that just means that the object is sufficiently close to the Earth's surface or any surface that we're dealing with. Okay. Values of delta y and delta Eg are positive if the displacement is upward and negative if the displacement is downward. Okay, that might be something to keep in mind as you start working through some of these questions. Right. So all that means is, if I'll write it so that you guys, this is me doing this on the fly here. I'll write it so that it kind of locks itself in there. Higher heights is like increasing, right? Positive. So we increase potential. And if we go down to lower heights, they're negative, we decrease. Okay? So, I started with a harder question. I don't know why. But I started with a harder question relative to, I think, the second one. The second one's a little bit easier. Okay. So we've got our typical inclined plane, because we've seen lots of this with the forces, right? And we've got a 68.5 kilogram skier rides a 2.5 kilometer ski lift from the base of the mountain to the top. Okay. The lift is at an angle of 13.9 degrees to the horizontal. We want to determine what the skier's gravitational potential energy is at the top. Okay. So I'm just going to draw myself a little free body diagram. Right. And the ski lift goes, well, we know it's at 13.9 degrees. And we've got the rider going up the mountain, right? And we know that the distance is 2.5 kilometers, right? Up there. Okay, so we know the ski lift. I'll put the, how do I want to denote this? We'll say it's D. What did I put my note? Doesn't really matter. 2.56 kilometers. That'll be the D value, right? That's the total distance of the trip. Now, down here, you guys will know, this is dx, and this over here, if I was able to draw this, that would be dy, okay? Is everybody following? So this is like the y component of the distance, and this will be the x component of the distance, okay? Now, we want to find out, determine the gravitational, or like the skier's gravitational potential energy, right? So we want to know, you know, after the rider gets to the top, right? It's up here now, right? What's the potential energy? Well, remember, I don't really care. I don't really care about dx, how far they traveled in the x direction, right? What I care about is their change in height, right? So let's say, okay, well, initially they were down here at the height of 0 on the ground, and now they're up here, right? This would be h2, right? So how do we find this, right? What's the equation tell us to say? Well, the equation tells us that, like, the EG, or gravitational potential energy, that's going to be equal to mgh, right? What is h? H in the context of our question is going to be the dy, right? So EG mg dy. So the only thing we know the skier's mass, and we know the g value. What do I have to solve for? Dy. Well, how do I find dy? Well, same way you guys did all your component work, right? You guys know that the dy value, that's opposite, right? So what's the deal? Okay, well, we know we're going to use sine, right? Because according to SOHCAHTOA, sine goes with the opposite, and oh, we know the hypotenuse, right? So we're going to say, okay, we're going to say sine of 13.9 degrees is equal to opposite over hypotenuse. So let's fill in the things we know. Well, sine of 13.9 is going to equal to dy, that's opposite, and the hypotenuse I know is being 2.56 kilometers. Okay, and now we can go, okay, well, I just want dy by itself. Multiply both sides by 2.56. So dy is going to equal 2.56 sine 13.9. So we just need a number for that. And you should get let me do it. In my solution, I converted to meters. It doesn't matter too much, though. Oh, no. Sorry, guys. Sorry. It does. It does matter. It does matter. Why does it matter, you might ask? I have kilometers, and what's G? What are the units? This is me going back to dimensional analysis. That's how I know I have to convert this. It's some of the little trick that you guys have to know. If I go meters per second squared, and I multiply that by kilometers, nothing's going to happen. Right? I need this in meters. That's how I clued in. Okay, so what is 2.56 kilometers in meters? Well, we just move this 1, 2, 3 to the right. So I get 2,560 meters. Okay, that's what goes down there. That's my bad. And then we'll get a number. When we type that number in, you should see 614.98. Are we okay? It's important to pay attention to the units. That's why I showed you that at the very first thing. Right? This doesn't work because you can't just plug the kilometers in there and get a number because the dimensions don't work. Okay, you gotta make everything match. That's how you know when to convert things. Typically, it's always meters and meters per second squared, kilograms, right? I should have just prompted me. Okay, so we're not quite done. We gotta actually plug this number in, but then we get a potential energy of this object, right? Joules and joules, right? So we're going to see gravitational potential energy should be equal to 9.8 and the mass. We'll put it in order. I'm trying to do two things at once. 68.5 times 9.8, decimal there, times the delta D value, 614.98. You should get that's a lot of potential energy. Doesn't mean much to you right now, but you know what does mean something to you. Obviously, as you guys, and this is what we're going to do tomorrow. We're going to raise objects to heights, and then we're going to let them go down, right? And we're going to see, okay, well, what's a lot of potential energy? I don't know. You guys don't know either, right? I think what's easier to contextualize is velocities, like how fast something's moving, right? So if I say that that thing is able to, or the skier is able to convert all of that potential energy, which isn't 100% true, because you're going to lose some energy to friction with the skis. But let's just say it was frictionless. What would be the velocity that that skier could reach by the end of the hill? Right, that's something that we could solve tomorrow, right? And then we get a context as to like, holy, being 614.98 meters above where you started, that's a lot of potential energy, right? It's tough to contextualize that number, right? Until we've actually done some like work around that. That's a big number, 4.13 times 10 to the 5, okay? Anybody have any questions with that one? So that's not as complicated as like an inclined plane force question, right? You just have to like figure out, okay, well, I need to figure out what the dy value is. How high up? That should be when you see potential energy, gravitational potential energy, you should be thinking height, right? The change in height controls that. Okay, we got one more to do. This one's a little bit easier. Okay, so let's scroll down if nobody has any questions. So a high jumper clears the pole, should be an S there, at a height of 2.3 meters, then falls safely back to the ground. Okay, the change in the jumper's gravitational potential energy from the pole to the ground is negative 1,650 joules. Okay, we want to figure out what the jumper's mass was. Okay, it's negative because we're measuring from the point in time that the jumper was just over the bar until they fell down to the mat. So they went from a high potential to a lower potential, right? High height to low height. And so we're going to see a decrease in the amount of potential energy. That's why our number is negative, right? If, just going back, if we were talking about the absolute value, then this number would be positive. But that's not energy, okay? The sign on energy tells us whether or not we've gained or lost energy. Okay, so we're not dealing with the sign means something, so we can't deal with the absolute value. It's almost like direction, right? When we drew the absolute value bars on magnitude, we knew how big something was, but like you can imagine if I just wrote 16, now that we've talked about this, 16, get off eraser, 1650 joules with an absolute value bar. Is that positive or is it negative, right? Did the object gain energy or did it lose? We don't know, right? That's why we don't do that, right? Okay, so we know its gravitational potential energy is that. It lost energy, right? We also know, we went from, if we looked at, and this is a key part too, so this is just a little subtlety, right? But you guys need to know this. We're looking at, like if I wrote the equation out, I'm just going to write the equation. Eg is mg delta h. We'll use height here for h for height, sorry. Right? We're looking at the change in height. Well, where did we start? Well, we're interested in when the jumper was above or just cleared the pole, and then their second value was when they hit the mat, right? So h1 is going to be the 2.3 meters above the ground. And h2 is going to be 0. We'll call that 0. Okay. So delta H, you guys know, as being H2 minus H1. Eg is equal to mg, and what is delta H? Delta H is H2 minus H1. Well, you just plug in the numbers, right? We know all this information, right? This is how this comes out to be negative, is when your H value, when your finishing point is lower than your initial point. And we're going to see that when I plug in the numbers, right? H2 is you want to plug in the numbers? I'll plug in the numbers. But we need the mass. We need that 9.8, and we need to go 0 is the final height. Take away the initial height. Right? And I suppose we could replace EG with our number here. Any questions? So, I get you guys do the number on that, whatever that number is, or you can just divide both sides by right? That'll cancel, cancel, cancel. M equals whatever this is. I probably already did it. It'd be negative 1650 divided by negative 23.13. I think the trick to these questions, much like when we were doing the kinematic questions, right, where we had the change in or delta dy's, I suppose, dy's or change in height, these are equal to each other. The trick is knowing whether or not something finished above or below where it started. Okay? That's the only trick to these questions, I think. Right? And then seeing whether or not your energy values or your potential energy come out positive or negative. That indicates whether or not something has increased or decreased its energy. Does anybody have any questions? That's it for the lesson. Okay.